Today, we're tackling one of the really rewarding areas of quantitative modeling, predicting risk itself. So our mission here is to get a solid grasp on the core theory behind autoregressive conditional heteroskedasticity and its successor, GARCH. For a long time series models were all about predicting the average, the conditional mean.
Right.
But what if the spread around that average, the uncertainty, is what really drives decisions? That's the shift we're looking at. Modeling the conditional second moment, predicting volatility.
And that shift, modeling variance, is something that changes over time and is importantly predictable. That absolutely revolutionized financial econometrics.
Yeah.
This whole framework really kicked off with Robert Engel's ARCH models back in '82. It was such a fundamental change that, as you mentioned, it led to him sharing the Nobel Prize in Economics in 2003.
Wow.
It basically established volatility not just as random noise, but as a dynamic process you could actually forecast.
Okay, so let's dig into the problem itself, the one that needed that Nobel-level solution. Conditional heteroskedasticity. It sounds complex. What does it actually mean for a time series?
Well, it means the variance. Think of it as the instability or the wobble in the series isn't constant. It changes. And crucially, it changes based on what happened recently.
Ah, okay.
So think of it like this. The size of yesterday's surprise or shock gives you a clue about the size of today's potential surprises. If there was a huge market swing yesterday,
You'd expect more potential for big swings today.
exactly, you should expect variability to be higher in the near term. So the variability is conditional on that history.
Got it. Now, you mentioned finance. When we model financial data, standard practice isn't to model the prices directly, right? We always seem to focus on returns. Why is that?
That's a key point. We almost always use logarithmic returns. You calculate them as the difference between the log of prices over time.
And why log returns specifically?
They just have much nicer statistical properties for modeling. Simple returns have limits, but log returns, they're unbounded. They can range from negative infinity to positive infinity. And importantly, they tend to look more like a normal distribution than raw prices or simple returns do.
Okay, that makes sense. A better starting point for the models.
Precisely.
And when you actually look at these return series, they tend to show these common behaviors, these stylized features, as they're called. I guess ignoring these would lead to pretty bad models.
Absolutely flawed models. Yes. And the most famous feature is something called volatility clustering.
Volatility clustering, what does that look like?
It's simply the observation that big price changes up or down, doesn't matter, tend to cluster together. And quiet periods, small changes, also tend to cluster together.
So periods of high anxiety followed by periods of relative calm and back again.
Exactly that. High volatility follows high volatility, low follows low. It's not random scatter.
It sounds a bit like, say, aftershocks from an earthquake. You get the big one, then a series of smaller or sometimes still large ones clustering afterwards.
That's a decent analogy. That clustering is the core signal we're trying to model the dependence and the variance. But it's not the only feature. Another big one is heavy tails.
Heavy tails. Why does that matter so much, especially for practitioners?
Because it means extreme events, market crashes, huge rallies. Things far out in the tails of the probability distribution happen much more often in the real world than a standard normal bell curve distribution would suggest.
Ah, the classic black swan problem almost.
Sort of. If you build your risk model assuming normality, you will consistently, and perhaps dangerously, underestimate how likely these extreme moves are. That has real-world consequences for risk management, for capital allocation.
Right, huge implications. Okay, what else? You mentioned clustering, heady tails.
There's also asymmetry. How the market reacts can depend on whether the news is good or bad.
So not a symmetric response.
Often not, especially in stocks. We often see a slight negative skew. Bad news tends to generate a bigger volatility spike than good news of the same magnitude.
Interesting. Like the market gets more jumpy on the way down.
That's the intuition. It's sometimes called the leverage effect in equities, although the idea of asymmetry is a bit broader than just that specific mechanism.
Okay. And there were a couple more features related to time, I think.
Yes, two more. First, aggregational Gaussianity. This is basically the central limit theorem in action. If you look at returns over longer periods, say monthly instead of daily, they tend to look more normally distributed. At the extremes average out somewhat.
Okay.
And finally, and this is really crucial for diagnosing the need for these models, long-range dependence in the variance.
Dependence in the variance, not the returns themselves.
Exactly. The returns day-to-day might look uncorrelated. Knowing today's return doesn't really help you predict tomorrow's return. But If you look at the squared returns, or the absolute value of return.
The magnitude of the changes.
Yes. Those often show very persistent autocorrelation, meaning the size of today's shock is related to the size of yesterday's and the day before's and so on, stretching back quite a while. That persistence in the squared series is the giveaway that the volatility itself is dependent on its past.
That distinction, uncorrelated returns but correlated squared returns, feels like the absolute heart of why ArchGH is needed.
It really is.
So how did Engel's original RCH model, let's say RCH, translate that observation into a mathematical form? How does it capture that dependence?
Okay, conceptually, the RCH model defines today's return as basically two pieces multiplied together. One piece is just a random shock, some unpredictable noise drawn from standard distribution, usually assumed normal initially.
Okay, the random part.
The other piece is a scaling factor, which changes over time. And that scaling factor is the conditional standard deviation. The model gives us an equation to predict the variance.
And how does it predict that variance?
It says the current conditional variance is equal to some baseline constant level plus a weighted sum of the squared values of the past.
So it directly uses the squared value of recent shocks to forecast today's expected level of variance.
Precisely. The magnitude of past surprises directly informs the prediction of current uncertainty.
And there are constraints on those weights, right, to make sure the variance prediction makes sense.
Absolutely vital. Since variance can't be negative, the baseline constant term has to be positive, and all the weights attached to those past squared returns must be non-negative. 0 is okay, but not negative.
Got it. Keeps the whole thing mathematically stable and interpretable as a variance.
Correct.
Now, you made a really interesting theoretical point earlier. You said the ARCH process itself, the returns it generates, is technically white noise. That seems counterintuitive if it has all this structure. Can you unpack that?
Yeah, it sounds weird, but it's key. If you just looked at the sequence of returns and you calculated their average, it would be 0. If you calculate the correlation between today's return and yesterday's return, or any past return, that correlation would also be 0.
So it looks completely random and unpredictable, like standard white noise.
In terms of its mean structure, yes, it fulfills the definition of white noise. 0 mean, 0 autocorrelation. The structure isn't in the first moment the mean or the simple correlations. It's hidden deeper.
Where?
It's in the conditional variance. The scaling factor, sigma explicitly, depends on the past values of the series. So while the returns appear uncorrelated level-wise, their predictive distribution is constantly being scaled up or down based on recent history. The dependence isn't gone, it's just shifted from the mean structure into the variance structure.
That's a fantastic explanation. So the correlation is sort of pushed down into the volatility. Okay, so if RCH uses squared returns, what led Bolerslev to generalize this in 1986? Why add another layer?
Well, empirically, people found that to capture the really long-lasting persistence of volatility we see in financial data, that long-range dependence in squared returns we talked about, you often needed a very large RCH model.
Like ARCH 20 or something.
Easily, maybe even higher.
Yeah.
And having that many parameters, all those weights for past squared returns, becomes computationally difficult. Estimation can get unstable, and it's just not very parsimonious, not very elegant.
Okay, so RCH worked in theory, but could be clunky in practice for persistent volatility. How did Garci fix that?
Garci took inspiration from RMA models used for the mean. Boleslav added another term to the variance equation.
What did he add?
He added lag values of the conditional variance itself.
Yeah.
So the GRCHQ equation says the current conditional variance depends on a constant plus the total lagged squared returns, like ARCH, plus the total lag values of the conditional variance.
Ah, so it's not just what were the recent shocks, but also what was our variance forecast yesterday and the day before.
Exactly. The model now has a memory of its own past volatility forecasts. This introduces a smoother, more persistent dynamic.
And that helps with the high-order problem.
Immensely. That added term, the lag variance, allows the model to capture long memory effects much more efficiently. Often, a simple GRCH model using just one lag squared return and one lag variance term can capture the kind of persistence that might need a very high-order ARCH model.
So much more parsimonious.
Far more. And empirically, GRCH has turned out to fit financial data incredibly well. It became, and arguably still is, the workhorse model in the field because of that balance of flexibility and efficiency.
Fantastic. Okay, theory makes sense. RCH captures shock dependence. GRCH adds variance memory for persistence. How do we actually use this? Say we have some time series data. How do we even know if we need an RCH or JRCH model? Is just looking at the squared returns and seeing clusters enough?
Looking is always the first step. Plot the returns, plot the squared returns. If you see that volatility clustering visually, that's a strong hint. But for rigor, we need a formal statistical test. We can't just eyeball it.
Right. Need to rule out random chance mimicking a pattern. What's the standard test?
The standard is the Lagrange multiplier test, often just called the LM test for ARCH effects.
Okay, the LM test. How does that work conceptually?
Conceptually, it's checking if the past squared residuals help predict the current squared residual. You first estimate your mean equation, maybe just a constant mean, maybe an ARMA model. Get the residuals from that model.
The errors, the unpredictable part from the mean model.
Exactly. Then you square those residuals. The LM test essentially involves running a regression. You regress the current squared residual on lagged squared residuals. The null hypothesis of the test is that all the coefficients on those lagged squared residuals are zero, meaning the past squared shocks have no predictive power for the current squared shock.
So if the test statistic is small and the p-value is high, we fail to reject that null.
Correct. In that case, the conclusion is no significant ARCH effects detected. Stick with your simpler mean model. The variance looks constant enough.
But if the test statistic is large, p-value small.
Then you reject the null hypothesis. You have statistical evidence against constant variance. You conclude that ARCH effects are present, and it's justified to proceed with estimating an RCH or GARCH model.
Okay, that gives us the green light. Once we decide to go ahead, how are the parameters of those weights in the RCH equations actually estimated? How do we choose the orders?
Estimation is typically done using the method of conditional maximum likelihood, MLE. It finds the parameter values that maximize the likelihood of observing the actual data, given the model structure.
Right, standard econometric technique.
For more careful work, you'd look at the autocorrelation, ACF, and partial autocorrelation, PACF, plots of the squared residuals from the mean model. They can give clues about appropriate orders, similar to how you use ACF, PCF for ARMA models.
Ah, okay.
Alternatively, you can estimate several candidate models and compare them using information criteria like AIC or BIC, which balance model fit against the number of parameters.
Right, finding that sweet spot between accuracy and simplicity.
Yeah.
Okay, let's try to synthesize this into a general modeling workflow. It sounds like a process.
Absolutely. It lays out a nice four-step process, which is pretty standard practice. Step one is crucial. Model the mean first. Before you even think about volatility, make sure you've adequately captured any predictable patterns in the level of the series. Is there a trend? Seasonality? Autocorrelation that an ARMA model can capture? Filter all that out first. You want the residuals from this mean equation to be as close to unpredictable noise as possible, at least in terms of their level.
So clean up the main signal first. What's step two?
Step two, test the residuals. Take those residuals from your best-fitting mean model, square them, and apply the LM test we just discussed. Check formally for ARCH effects.
If the LM test is insignificant,
You stop. Your work is done. The mean model is sufficient. The variance appears constant.
but if the test is significant,
Then you proceed to step three. Specify and estimate the volatility model. This is where you choose your GARCH. And then this is important. You perform a joint estimation. You re-estimate the parameters of the mean equation and the volatility equation together using MLE.
not separately. You estimate the whole system at once.
Yes, because the volatility affects the likelihood function used for estimating the mean parameters too. They're intertwined.
Okay, mean model, test residuals, joint estimation. What's the final step? Step four.
Step four is diagnostics and refinement. Check the model you just estimated. Does it look good? Specifically, look at the standardized residuals. These are the residuals divided by the estimated conditional standard deviation from your GARCH model.
And what are we hoping to see in those standardized residuals?
Ideally, they should look like pure random noise now. They should be roughly independent and identically distributed, i.e., hopefully close to a standard normal distribution. And importantly, they should not show any remaining volatility clustering. You check their ACF-PACF plots, especially the squared standardized residuals.
But you mentioned earlier that things can still go wrong here related to the heavy tails.
Exactly. Very often, even after fitting a GARCH model that captures the clustering, the standardized residuals still fail tests for normality. They still exhibit excess kurtosis, those heavy tails we discussed earlier.
So fix the clustering, but not the underlying shape of the shocks.
Precisely. The model captured the time-varying scale of the shocks, but assumed the scaled shocks were normal, and maybe they just aren't.
So if our standardized residuals are still too fat-tailed, what's the refinement? How do we fix that?
The most common refinement is to change the assumption about the distribution of that underlying random noise term. Instead of assuming it's normally distributed, we assume it follows a distribution that naturally has heavier tails.
Like what?
The most popular choice is the standardized student's t-distribution. By estimating its degrees of freedom parameter along with the GARCH parameters, you allow the model to explicitly account for the observed fat tails in the data.
So you keep the GARCH-PIC-Q structure for the variance dynamics, but you swap out the assumed distribution of the basic shocks.
Exactly. It doesn't change the core mechanism for modeling the conditional variance, but it makes the overall model provide a much more realistic description of the data, especially the probability of extreme events. That's critical for accurate risk forecasting.
That makes a lot of sense. It shows the flexibility of the framework, and this basic GARCH idea has been extended even further, hasn't it?
Oh, massively. The literature exploded. You have models like iGARCH, integrated GARCH, for cases where volatility shocks seem permanent. You have eGARCH, exponential GARCH, and tGARCH, threshold GARCH, designed specifically to capture that asymmetry effect, the different impact of positive versus negative shocks. The list goes on and on. It's a huge field.
It really sounds like it. This has been a fantastic deep dive into the architecture of risk modeling. I think the key takeaway for you, the listener, is that GARCH models provide this powerful theoretical framework to actually model and forecast uncertainty itself. It's not just static noise, it's dynamic.
Yeah.
And the strategy is clear. First, deal with the mean structure, then model the volatility structure left over in the residuals.
Absolutely. And while, yes, this all started in finance because the need was so obvious there, the underlying principle that volatility clusters, that big changes can breed more big changes that's potentially universal, we're seeing these models used in environmental science now for things like wind speed volatility, which impacts renewable energy.
Interesting.
So it really prompts a question for you to think about. Beyond finance, beyond the obvious places, where else in science or business or any data-rich field you work in, are there processes governed by this kind of time-varying clustered uncertainty? Are there places where you're currently using models assuming constant variance, but we're adopting this kind of conditional framework like GARCH could unlock deeper insights or better forecasts?